modeling an autoregressive process. In the previous chapter, we explored moving average, MA, processes where the current value of a time series is modeled as a linear combination of past error terms. We observed that MA models exhibit a finite memory, meaning their influence on future values diminishes rapidly, typically cutting off after a specific number of lags in the autocorrelation function, ACF, plot. While effective for certain types of time series, many real-world phenomena exhibit a different kind of dependency. Their current values are directly influenced by their own past values. This is the realm of autoregressive, AR, processes. Understanding the autoregressive concept. An autoregressive, AR, process is a time series model where the current observation, code snippet, is expressed as a linear combination of its past observations and a white noise error term. The term autoregressive literally means regressing on itself, emphasizing that the series' future values are predicted using its own past values. Consider a simple example, predicting tomorrow's stock price based on today's and yesterday's prices. This is distinct from an MA model, where you might predict based on the magnitude of past prediction errors. In an AR model, the direct history of the series itself is the primary driver. The AR-P notation. Autoregressive models are denoted as code snippet, where code snippet signifies the order of the autoregressive process. The order code snippet indicat is the number of past observations, or lags, that are included in the model to predict the current value. And code snippet process means that the current value code snippet is primarily influenced by the immediately preceding value code snippet. And code snippet process means code snippet is influenced by code snippet and code snippet. Generally, encode snippet process implies that code snippet depends on code snippet. The general mathematical form of encode snippet process is code snippet. Here, code snippet is the current observation. Code snippet is a constant term, intercept. Code snippet are the autoregressive coefficients, which quantify the strength and direction of the influence of past observations. Code snippet are the past observations at lags 1 to code snippet. Code snippet is the white noise error term, representing random fluctuations not explained by past values. Distinguishing AR from MA using ACF and PACF plots. One of the most crucial steps in identifying the appropriate time series model is analyzing the autocorrelation function, ACF, and partial autocorrelation function, PACF plots. These plots reveal the underlying correlation structure of the series. Recap, MA model signatures. ACF for MA. Cue the ACF plot for a moving average process of order code snippet will show significant spikes, correlations, at lags up to code snippet, and then cut off abruptly, i.e., correlations become non-significant, at lags greater than code snippet. This R reflects the finite memory of MA processes. PACF for MA. Cue the PACF plot for an MA process will typically decay slowly, either exponentially or sinusoidally. AR model signatures. The decaying ACF. ACF for AR, P in stark contrast to MA processes. The ACF plot for an autoregressive process of order code snippet will typically show a slowly decaying pattern. This decay can be exponential, smoothly tapering off, or sinusoidal, oscillating before tapering off. Why does the ACF decay for an AR process? Consider in code snippet process, code snippet. 1. Code snippet is directly correlated with code snippet due to code snippet. This strong correlation shows up at lag 1 in the ACF. 2. Code snippet is also correlated with code snippet, since code snippet itself depends on code snippet. 3. Because code snippet depends on code snippet and code snippet depends on code snippet also has an indirect correlation with code snippet. This indirect correlation is weaker than the direct one. 4. This chain of dependencies continues. Code snippet is indirectly correlated with code snippet through code snippet, and so on. Each step further back in time weakens the overall correlation, causing the ACF values to gradually diminish rather than abruptly cut off. This creates the characteristic decaying pattern. If the code snippet coefficients are negative or if there are multiple AR terms. This decay might be oscillatory or sinusoidal, indicating alternating positive and negative correlations that gradually die out. PACF for AR. The PACF plot for an autoregressive process of order code snippet will show significant spikes at lags up to code snippet and then cut off abruptly, i.e., correlations become non-significant at lags greater than code snippet. Why does the PACF cut off for an AR process? The partial autocorrelation function measures the direct correlation between an observation and a lagged observation after removing the effects of the intermediate lags. For an code snippet process, the current value code snippet is directly dependent only on the previous code snippet values, code snippet. Once the influence of these code snippet direct lags is accounted for, any further lags, code snippet, etc., have no additional direct correlation with code snippet. Therefore, the PACF effectively isolates the order code snippet by showing a sharp cutoff. This distinct behavior of ACF, decaying, and PACF, cutting off, is the primary visual cue for identifying an AR process and determining its order code snippet. What's next? In the following sections, we will delve deeper into the practical aspects of modeling autoregressive processes. Formal definition and properties. We will mathematically define AR processes, discuss their stationarity conditions, and explore their theoretical properties. Identifying the order code snippet. We will learn how to systematically use the PACF plot to determine the appropriate order. Code snippet for an AR model based on empirical data. Fitting AR models. We will walk through the process of estimating the coefficients, code snippet values, of an AR model using Python libraries like code snippet. This will involve preparing time series data and interpreting model output. Forecasting with AR models. Finally, we will apply our fitted AR models to generate future forecasts, evaluate their accuracy, and understand their limitations in real-world scenarios. Predicting the average weekly foot traffic in a retail store. Understanding and predicting future trends is paramount for businesses to optimize operations, manage resources, and make informed strategic decisions. For a retail store, forecasting average weekly foot traffic is a critical application of time series analysis. Accurate predictions allow store managers to optimize staff scheduling, ensuring adequate coverage during peak hours while minimizing unnecessary labor costs during quieter periods. It also aids in inventory management, marketing campaign planning, and overall store layout optimization. This section delves into a practical case study, forecasting weekly foot traffic. We will follow the standard workflow for time series model identification, emphasizing the steps necessary to prepare data for autoregressive AR modeling and introduce a new crucial tool, the Partial Autocorrelation Function, PACF. 1. Understanding the problem and initial data exploration. Our objective is to forecast the average weekly foot traffic for a retail store. We'll start by examining historical data. For educational purposes, we will generate a synthetic dataset that mimics realistic foot traffic patterns, including a clear upward trend, which is common in growing businesses or expanding markets. Generating synthetic foot traffic data. Real-world datasets can be complex and sometimes proprietary. For learning purposes, generating synthetic data allows us to create specific patterns, like trends or seasonality, that illustrate key concepts effectively. Here, we'll create a dataset with a clear upward trend and some random noise, representing weekly foot traffic over several years. Download the code on one PageCode Substack. The code above initializes our time series by creating a code snippet named code snippet. We generate a sequence of weekly dates for 5 years. The code snippet component creates a linearly increasing trend, simulating growth. We then add code snippet using a normal distribution to mimic random fluctuations and a code snippet to introduce annual patterns, such as higher traffic during holiday seasons. Combining these elements results in our synthetic code snippet time series. Visualizing the time series. Visualizing the raw time series is the crucial first step in any time series analysis. It allows us to observe patterns such as trends, seasonality, and unusual spikes or drops, which are key indicators for subsequent modeling steps. Download the code on one PACF Substack. This plot, similar to what might be presented as Figure 5.1 in a textbook, immediately reveals key characteristics of our data. We can clearly observe an upward trend, indicating that foot traffic is generally increasing over time. This visual cue is vital for assessing stationarity, a fundamental concept in time series analysis. 2. Assessing stationarity. Most classical time series models, including autoregressive AR models, assume that the underlying G process generating the data is stationary. A stationary time series is one whose statistical properties, like mean, variance, and autocorrelation, do not change over time. Why is stationarity important? Model simplification. Stationary series are easier to model because their behavior is consistent over time. Reliable forecasting. If a series is non-stationary, statistical models fitted to it might produce unreliable forecasts as the relationships between observations change over time. Parameter stability. The parameters of stationary models are constant, making them more interpretable and stable. Visually, a series with a clear trend or varying variance, heteroscedasticity, is non-stationary. Our foot traffic plot clearly shows an upward trend, suggesting non-stationarity. While visual inspection is a good starting point, formal statistical tests are necessary for a more rigorous assessment. The Augmented Dickey-Fuller ADF test. The Augmented Dickey-Fuller ADF test is a widely used statistical test to check for stationarity in a time series. It's a type of unit root test. Null hypothesis: H0 the time series has a unit root, meaning it is non-stationary. Alternative hypothesis: H1 the time series does not have a unit root, meaning it is stationary. To interpret the test, we look at the p-value. If the p-value is greater than a chosen significance level, e.g. 0.05, we fail to reject the null hypothesis, concluding that the series is non-stationary. If the p-value is less than or equal to the significance level, we reject the null hypothesis, concluding that the series is stationary. Download the code on one PACF Substack. The output of the ADF test confirms our visual observation. The p-value is high, e.g. 0.999, indicating that the code snippet series is indeed non-stationary. This means we need to transform the data to achieve stationarity before applying most AR models. 3. Achieving Stationarity. Transformations differencing. Since our series is non-stationary due to a trend, the most common and effective transformation is differencing. Differencing involves computing the difference between consecutive observations. This operation helps remove trend and seasonality, making the series stationary. What is differencing? A first-order difference is calculated as $white equals YT, YT, $1. This effectively removes a linear trend. If the series still exhibits non-stationarity after first differencing, e.g., if it has a quadratic trend, a second-order difference might be applied. $YT equals white, $. For our foot traffic data, which shows a clear linear trend, a first-order differencing is typically sufficient. Download the code on one PACF Substack. After differencing, the plot of code snippet should appear much more stable, without a clear upward or downward trend. The mean should hover around 0, and the variance should appear more constant. Retesting stationarity after differencing. It's crucial to re-RU in the ADF test on the difference series to confirm that stationarity has been achieved. Download the code on one PACF Substack. Now, the p-value for the difference series should be significantly lower, e.g., less than 0.05, allowing us to reject the null hypothesis and conclude that the series is stationary. This confirms that differencing has successfully removed the trend. 4. Identifying model order. Autocorrelation function, ACF, and Partial Autocorrelation Function, PACF. Once our time series is stationary, we can proceed to identify the order of the autoregressive AR process. For this, we rely on two powerful tools, the autocorrelation function, ACF, and the Partial Autocorrelation Function, PACF. Autocorrelation Function, ACF. The ACF measures the correlation between a time series and its lag values. For a stationary series, the ACF helps us understand the extent to which past values influence current values. For an autoregressive, AR, process, the ACF typically exhibits an exponential decay or a sinusoidal pattern. This decay indicates that the correlation gradually diminishes as the lag increases. It is not cut off abruptly, unlike the PACF for an AR process. A common point of confusion: a slowly decaying ACF in a non-stationary series is often the visual cue that differencing is needed. Once differenced and stationary, an AR process's ACF will still decay, but it's the PACF that provides direct information about the AR order. Partial Autocorrelation Function, PACF. The PACF measures the correlation between an observation and a lagged observation, after removing the effects of the intermediate observations. For example, the partial autocorrelation at lag 3 is the correlation between $YT and $Y3 that is not explained by the linear dependence on $Y, $1, and $Y2. The PACF is particularly useful for identifying the order of an autoregressive AR model. For an AR, P, process, the PACF will show significant spikes at lags 1 through code snippet and then cut off, become non-significant at lags greater than code snippet. Plotting ACF and PACF. Let's plot the ACF and PACF for our differenced stationary foot traffic data. Download the code on one patch code Substack. When interpreting these plots, ACF plot, look for the pattern of decay. For a purely AR process, it should decay exponentially. PACF plot, look for the cutoff point. The lag at which the PACF values become non-significant, fall within the blue shaded confidence interval, suggests the order code snippet for an AR P model. For our synthetic data, you might observe significant spikes at the first few lags, e.g., lag 1, 2, and then a drop into the confidence interval, indicating the likely AR order. For instance, if only lag 1 is significant, it suggests an AR1 process. If lags 1 and 2 are significant, it suggests an AR2 process. 5. Moving towards AR model building. Based on the interpretation of the PACF plot, we can determine the appropriate 8-order code snippet for our autoregressive model, denoted as ARP. An ARP model predicts the current value of the series based on a linear combination of its past code snippet values. The general form of an ARP model is $est égal C plus phi 1 Y T moins 1 plus phi 2Y T moins 2 plus phi pi Y TPO plus epsilon $, where $YT is the value of the series at time code snippet. $C is a constant. $phi 1 $fip are the model parameters coefficients that quantify the influence of past values. $epsilon is the white noise error term, representing random fluctuations not explained by the model. In the subsequent sections, we will use libraries like code snippet in Python to fit AR models based on the identified order code snippet and then evaluate their forecasting performance. The process of understanding the data, ensuring stationarity, and identifying the model order using ACF and PACF is foundational to building robust time series of forecasting models. Defining the autoregressive process. In our journey through time series modeling, we've explored how past error terms can influence current observations through moving average, MA, processes. Now, we shift our focus to a different, yet equally powerful, mechanism: how past values of the time series itself can predict current values. This concept forms the foundation of autoregressive, AR, processes. The core idea: regression of a variable on itself. The term autoregressive might sound complex, but it simply means regressing a variable on its own past values. Think of it like this. If you want to predict how much coffee you'll drink today, a very strong predictor might be how much coffee you drank yesterday, or even the day before. You're using your own past coffee consumption to predict your current consumption. In time series analysis, This translates to using a series' own lag values, values from previous time periods, as predictors in a regression equation. Unlike moving average models, which look at the influence of past random shocks or error terms, autoregressive models directly examine the linear relationship between the current observation and a certain number of its preceding observations. The general autoregressive model, ARP, an autoregressive process of order code snippet denoted as ARP, models the current value of a time series, $YT$, as a linear combination of its code snippet previous values, $Y10, Y2, \dots, $YTP$, plus a constant int. A white noise error term. The general mathematical expression for an ARP model is $YT equals C plus \phi1y, 1 plus \phi2yt, 2 plus dots plus \fit ytp plus $. Let's break down each component of this equation to fully understand its meaning and significance. $YT$. This represents the current observation of the time series at time code snippet. It is the value we are trying to model or predict. For example, if we're forecasting retail foot traffic, $YT$ would be the foot traffic this week. $C$. This is the constant term, also known as the intercept or drift. It represents the baseline value of the series when all past values are zero, or more generally, it accounts for a non-zero mean in the series. If $C$ is non-zero, it suggests a systematic upward or downward trend or a long-term average that the series tends towards. We'll explore its implications further when discussing the random walk. $\phi1, \phi2, \dots, \fit$. These are the autoregressive coefficients. Each $\phi$ measures the linear impact of the code snippet th lagged observation, $YTI$, on the current observation, $YT$. For instance, $\phi1 quantifies how much of $YT1, the value from the previous period, contributes to $YT$. These coefficients are crucial because they dictate the persistence and pattern of a time series. Positive coefficients suggest that a high value in the past leads to a high value now, while negative coefficients suggest an oscillatory or mean-reverting behavior. $YT -1, YT2, \dots, YTP$. These are the lag values of the time series. They represent the observations from code snippet period ago, code snippet periods ago, up to code snippet periods ago. These are the regressors in our autoregression. $P$. This is the order of the autoregressive process. It indicates the number of past observations that are included in the model to predict the current value. An AR1 model uses only the immediately preceding value, $YT, $1. An AR2 model uses the two preceding values, $YT, $1, and $YT, $2. The choice of code snippet is critical and often determined by analyzing the autocorrelation function, ACF, and partial autocorrelation function, PACF, of the time series, which we will cover in subsequent chapters. $\epsilon$. This is the error term, also known as the residual or innovation at timecode snippet. It represents the portion of $YT$ that cannot be explained by the linear combination of its past values. It captures all the random, unpredictable fluctuations in the series. For a valid AR model, this error term is assumed to be white noise. Special cases, AR1 and AR2 models. Understanding the general ARP model is key, but it's often helpful to look at its simplest forms to build intuition. The AR1 process, an autoregressive process of order 1, or AR1, is the simplest form of an AR model. It states that the current value of the series depends only on its immediately preceding value and a random error. The mathematical formulation for an AR1 model is $$ est égal C plus phi 1 Y t moins 1 plus epsilon $. Here, the current value $YT$ is a linear function of the previous value $YT, $1, plus a constant $C$ and a white noise error $\epsilon$. The coefficient $\phi1 determines the strength and direction of the relationship between consecutive observations. The AR2 process. An autoregressive process of order 2, or AR2, extends the AR1 by including the second lag as a predictor. The mathematical formulation for an AR2 model is $$ est égal C plus phi1 y t moins 1 y plus phi2y t moins 2 y plus epsilon $. In this model, $YT$ depends on both $YT1 and $YT2. The coefficients $\phi1 and $\phi2 capture the influence of these two immediate past values. An AR2 model can capture more complex patterns than an AR1, such as oscillations or cycles that might not be apparent from just the previous period. AR1 and the random walk, a special relationship. One of the most important insights for understanding AR1 processes is their direct link to the random walk model, which we briefly touched upon previously. A random walk model is defined as $YT igual a T1 más barra inversa epsilon $. Comparing this to the AR1 equation, $YT equals C plus \phi1 YT, 1 plus \epsilon $. We can see that a random walk is a special case of an AR1 model where the constant term $C$ is equal to 0. The autoregressive coefficient $\phi1 is exactly 1. This means that if $\phi1 equals $1, the current value is simply the previous value plus a random shock. T series has no tendency to return to a mean. It can wander indefinitely. Implications of the constant $C$ drift. If we consider an AR1 model where $\phi1 equals $1, but the constant $C$ is non-zero, $YT equals C plus YT, 1 plus \epsilon $. This is known as a random walk with drift. In this scenario, the series still wanders randomly, but on average, it drifts upwards or downwards by the value of $C$ in each period. For example, if $C$ represents an average daily increase in stock price, the stock price would tend to rise by $C$ each day, on top of its random fluctuations. This is particularly relevant for modeling phenomena that exhibit a sustained trend, such as economic growth or population increase. The error term, white noise assumption. A fundamental assumption for the error term $epsilon$ in an ARP model, and indeed in many time series models, is that it must be white noise. This means that the error term satisfies the following properties. 1. Zero mean, $epsilon equals $0. On average, the error should not systematically push the series up or down. 2. Constant variance, $var epsilon equals \sigma $2. The variability of the errors should be consistent over time, meaning there are no periods of unusually high or low volatility. This is also known as homoscedasticity. 3. No autocorrelation, $COV epsilon equals $0 for all $K nec $0. The error at any given time code snippet should not be correlated with errors from any other time period. This ensures that all the predictable information from past values has been captured by the AR terms, and only random, unpredictable noise remains in the error term. If the error term is not white noise, it implies that there is still some systematic pattern or information left in the residuals that could be modeled, indicating that the AR model is not fully capturing the underlying process. A critical property, stationarity. For an ARP process to be stable and predictable in the long run, it must be stationary. A stationary time series is one whose statistical properties, like mean, variance, and autocorrelation, do not change over time. This is a crucial concept because many statistical techniques for time series analysis assume stationarity. Non-stationary series often exhibit trends or changing variance, making them difficult to model and forecast reliably. For an AR1 process, $yt equals c plus backslash phi1 y 1 plus backslash epsilon dollar. The condition for stationarity is that the absolute value of the autoregressive coefficient $backslash phi1 must be less than 1, i.e. $backslash phi1 less than $1. If $backslash phi1 less than $1, any shock to the system will eventually die out and the series will tend to revert to its mean. If $backslash phi1 equals $1, as in a random walk, the series is non-stationary and shocks have a permanent effect. If $backslash phi1 greater than $1, the series is explosive. Any shock will be amplified over time, leading to an ever-increasing or decreasing trend. For an AR2 process, $yt equals c plus backslash phi1 y 1 plus backslash phi2 yt 2 plus backslash epsilon dollar, the stationarity. Y conditions are slightly more complex, involving the roots of a characteristic polynomial. Specifically, the roots of the polynomial $1 backslash phi1l backslash phi2l squared equals $0, where L is the lag operator, must lie outside the unit circle or equivalently for the inverse roots inside the unit circle. This ensures that the influence of past values diminishes over time. Understanding stationarity is vital because it determines whether an AR model is appropriate for a given series and how its forecast will behave. We will delve deeper into testing for and addressing non-stationarity in later chapters. Looking ahead, this section has laid the theoretical groundwork for understanding autoregressive processes. In subsequent sections, we will move from definition to application. We will explore how to identify the appropriate order code snippet for an AR model, how to estimate its coefficients, and critically, how to simulate AR processes in Python to visualize their behavior. Simulating AR1 and AR2 processes with different $phi coefficients will provide concrete examples of how these parameters influence the time series patterns, reinforcing the concepts introduced here. We will also revisit our retail foot traffic example to apply these concepts in a practical forecasting scenario. Preparing and inspecting the time series data. Before we can determine the order of an autoregressive AR process, we must first ensure our time series data is properly loaded and understood. This initial step involves importing necessary libraries, loading the dataset, and performing a preliminary inspection to confirm its structure and content. Download the code on one patch code Substack. We begin by importing code snippet for data manipulation, code snippet for numerical operations, specifically for differencing, and code snippet for plotting. Crucially, we import code snippet from code snippet for stationarity testing, and code snippet from code snippet for visualizing autocorrelation functions. We also include a line to suppress warnings, which is often useful for a cleaner presentation in educational material. Download the code on one patch code Substack. Here, we load our code snippet dataset. It's essential to parse the date column as actual datetime objects and set it as the data frame's index. This step is critical for time series analysis, as it allows pandas to recognize the temporal ordering of our data. Inspecting the code snippet of the data frame provides a quick overview of the data, confirming column names, data types, and the range of values. This ensures the data has loaded correctly before proceeding with more complex analysis. Visualizing the time series. A fundamental step in any time series analysis is to visualize the data. This allows us to quickly identify obvious patterns such as trends, long-term increases or decreases, seasonality, repeating patterns at fixed intervals, and any significant outliers. These visual cues are often the first indicators of whether a series is stationary or non-stationary. Download the code on one patch code Substack. This code block generates a line plot of the code snippet data over time. We use code snippet to create a figure and an axis object, then plot the series. Setting appropriate titles and labels is crucial for interpretability. The code snippet and code snippet commands are particularly useful for time series plots, as they prevent date labels on the x-axis from overlapping, making the plot much more readable. From this visual inspection, we can observe if there's an upward or downward trend, or if there are recurring spikes or dips that suggest seasonality. For our code snippet data, we typically observe an upward trend, indicating non-stationarity. Testing for stationarity. The Augmented Dickey-Fuller (ADF) test. Stationarity is a core assumption for many time series models, including AR models. A stationary series has statistical properties, mean, variance, autocorrelation, that do not change over time. Non-stationary series often exhibit trends, seasonality, or a changing variance. The Augmented Dickey-Fuller (ADF) test is a formal statistical test used to check for stationarity. The ADF test has the following hypotheses. Null hypothesis, $H0 the time. Series has a unit root, i.e., it is non-stationary. Alternative hypothesis, $H1 the time series does not have a unit root, i.e., it is stationary. We reject the null hypothesis if the p-value is less than our chosen significance level, e.g., 0.05. If we reject $H0, it means the series is likely stationary. Download the code on one PACF Substack. We define a helper function code snippet to encapsulate the ADF test execution and result interpretation. This makes our code cleaner and more reusable. We then apply this function to our original code snippet series. When running code snippet, we pass code snippet to ensure any potential code snippet values, which can arise from operations like differencing later, are handled, although for the original series, this is not strictly necessary. The output provides the ADF statistic, the p-value, and critical values at different confidence levels. For the code snippet data, the p-value for the original series will typically be high, e.g., greater than 0.05, leading us to conclude that the series is non-stationary, consistent with our visual inspection. Achieving stationarity through differencing. If the ADF test indicates non-stationarity, we need to transform the series to make it stationary. A common and effective technique is differencing. First-order differencing calculates the difference between consecutive observations, $YT, $1. This effectively removes a linear trend. If seasonality is present, seasonal differencing can also be applied. Download the code on one PACF Substack. Here, we use code snippet to perform first-order differencing. This operation calculates $YT, $1 for each point. Note that code snippet returns a number py array, so we convert it back into a pandas code snippet and align its index with the original data frame's index, starting from the second element since the first difference results in one less data point. The resulting code snippet series represents the week-over-week change in foot traffic. Visualizing the difference series. After differencing, it's good practice to visualize the transformed series to see if the trend has been removed and if the series now appears more stable around a constant mean. Download the code on one PACF Substack. This code plots the code snippet series. Visually, this plot should appear much more stable, fluctuating around 0, without a clear upward or downward trend. This visual confirmation is a good preliminary indicator that differencing has been effective in achieving stationarity. Retesting for stationarity, ADF test on difference data. After differencing, we must formally retest the series for stationarity using the ADF test to confirm that the transformation was successful. Download the code on one PACF Substack. We rerun our code snippet function, this time on the code snippet series. For a successfully different series, we expect the p-value to be low, e.g., less than 0.05, leading us to reject the null hypothesis and conclude that the difference series is indeed stationary. If the series were still non-stationary, we might consider applying a second differencing step or seasonal differencing if seasonality is suspected. Autocorrelation Function, ACF, analysis for AR processes. Once a time series is stationary, the next step in identifying its underlying process, AR, MA, or ARMA, involves analyzing its autocorrelation structure. The autocorrelation function, ACF, measures the linear correlation of a time series with its lag values. For an autoregressive, AR, process, the ACF typically exhibits a slow, exponential decay or sinusoidal pattern. This is because an AR process directly depends on its past values, which in turn depend on their past values, leading to a ripple effect of correlations across many lags. Download the code on one patch code Substack. This code generates and displays the ACF plot for our stationary code snippet series. The code snippet function from code snippet handles the calculations and plotting. The blue shaded area represents the confidence interval. Any bars extending beyond this area are considered statistically significant. For an AR process, we look for a pattern where the autocorrelation values gradually decrease, either smoothly or with oscillations, rather than abruptly cutting off after a few lags, which would be characteristic of an MA process. Observing this exponential decay in the ACF plot for our different foot traffic data strongly yes. Suggests that an autoregressive component is present in the series. Partial Autocorrelation Function, PACF, analysis for AR order. While the ACF helps us identify the presence of an AR component through its exponential decay, it does not directly tell us the order code snippet of the AR process. For this, we turn to the Partial Autocorrelation Function, PACF. The PACF measures the correlation between an observation $YT and an observation at a previous lag $YTK, after removing the linear dependence of $YT on all intermediate observations, $YTK plus $1. In simpler terms, PACF tells us the direct correlation between $YT and $YTK, isolating the influence of the specific lag. For an autoregressive process of order code snippet, denoted AR-P, the PACF will show significant spikes at lags up to code snippet. The PACF will cut off to 0 or become non-significant after lag code snippet. This is the inverse behavior compared to MA processes, where the ACF cuts off and the PACF decays. Understanding this distinction is crucial for correctly identifying model orders. Download the code on one patch code Substack. This crucial code block generates the PACF plot for our stationary code snippet series. Similar to code snippet calculates and plots the partial autocorrelations. The interpretation for determining the AR order code snippet is straightforward. Identify the last significant spike, the last bar extending beyond the blue confid. Its interval, before the PACF values drop to non-significant levels. For example, if the PACF shows significant spikes at lag 1 and lag 2, but then drops into the confidence interval from lag 3 onwards, this suggests an AR-2 process. The code snippet value determined from the PACF plot will be used as the code snippet parameter when fitting an AR model, e.g., code snippet or code snippet, where code snippet is the order of differencing already applied. Conclusion: finding the AR order. To summarize the process of finding the order code snippet of a stationary autoregressive process. 1. Ensure stationarity. Visualize the time series and perform the Augmented Dickey-Fuller (ADF) test. If non-stationary, e.g., high p-value for ADF, apply differencing, e.g., code snippet, until the series becomes stationary, then retest with ADF. The number of differencing steps becomes the code snippet parameter in an ARIMA model. 2. ACF analysis. Plot the autocorrelation function, ACF, of the stationary series. If the ACF exhibits a slow, exponential decay or sinusoidal pattern, it indicates the presence of an autoregressive component. 3. PACF analysis. Plot the partial autocorrelation function, PACF, of the stationary series. The order code snippet of the AR process is determined by the lag where the PACF plot cuts off sharply to non-significant values, i.e., the last significant spike before values fall within the confidence interval. This systematic approach, combining visual InSP, tie-in with formal statistical tests and the distinct patterns of ACF and PACF plots, provide a robust methodology for identifying the appropriate order of an AR model for forecasting. 5.3.1 The Partial Autocorrelation Function, PACF. In the previous section, we established the mathematical definition of an autoregressive AR process with a current value of a time series is a linear combination of its past values and a white noise error term. A critical step in building an AR model is determining its order code snippet, which represents the number of past observations that directly influence the current observation. While the autocorrelation function, ACF, helps identify moving average, MA, processes by showing a sharp cutoff, it does not exhibit the same clear behavior for AR processes. For AR models, the ACF tends to decay gradually, making it difficult to pinpoint the exact order code snippet. This is where the Partial Autocorrelation Function, PACF, becomes indispensable. The PACF is specifically designed to help us identify the order of an AR process. Understanding what the PACF measures. The Partial Autocorrelation Function, PACF, measures the linear relationship between an observation and a lagged observation in a time series, after removing the linear influence of the observations at intermediate lags. To illustrate this distinction from the ACF at lag code snippet measures the correlation between code snippet and code snippet. This correlation includes both the direct effect of code snippet on code snippet and any indirect effects that pass through the intermediate observations code snippet. PACF at lag code snippet measures the direct correlation between code snippet and code snippet, effectively partialing out or removing the influence of code snippet. Consider an AR1 process code snippet. The ACF at lag 1 will be strong, reflecting the direct relationship. The ACF at lag 2 will also be non-zero, but this is because code snippet is influenced by code snippet, and code snippet is influenced by code snippet. So, code snippet has an indirect effect on code snippet through code snippet. The PACF at lag 1 will show a strong correlation, as expected. The PACF at lag 2, however, will be close to zero, non-significant. This is because once the effect of code snippet is removed, code snippet has no direct influence on code snippet in an AR1 process. This partialing out is crucial because for a pure ARP process, only the first code snippet lags have a direct influence on the current value. Lags beyond code snippet have only indirect influence, which the PACF removes, leading to a clear cutoff behavior. Simulating ARP processes and their PACF. To solidify our understanding, let's simulate some known ARP processes and observe their PACF plots. We'll use the code snippet library in Python, which provides powerful tools for time series analysis. First, we need to import the necessary libraries. Download the code on OnePageCode Substack. Here, code snippet is used for numerical operations and array creation, code snippet for plotting, code snippet from code snippet for simulating ARMAP, processes, and code snippet for generating PACF plots. Code snippet will be used for our real-world data example. To ensure our simulations are reproducible, we'll set a random seed. Download the code on OnePageCode Substack. Setting code snippet ensures that every time you run the code, the random numbers generated by code snippet are the same, leading to identical simulation results. This is vital for debugging and sharing your analysis. Simulating an AR1 process. An AR1 process is defined by code snippet. Let's simulate one with a coefficient code snippet. Download the code on OnePageCode Substack. Important note on code snippet coefficients. A common point of confusion when using code snippet is how to specify the code snippet coefficients. The code snippet class internally represents the AR polynomial as code snippet. Therefore, if your AR model is formulated as code snippet, you should pass the coefficients code snippet directly to the code snippet argument. The class handles the negation internally. Our code snippet correctly represents code snippet. Now, let's plot the PACF of our simulated AR1 series. Download the code on OnePageCode Substack. The code snippet function from code snippet is used here. We specify code snippet to view the PACF up to 20 lags. The code snippet specifies the Yule-Walker method for estimating PACF, which is a common choice. Interpreting the PACF plots shaded region. You'll notice a shaded blue region around 0 in the PACF plot. This region represents the confidence interval, typically 95%, for the partial autocorrelation coefficients. Any spike that extends beyond this shaded region is considered statistically significant at the chosen confidence level. If a spike falls within the shaded region, it means the partial autocorrelation at that lag is not significantly different from 0. For an AR/P process, we expect code snippet significant spikes, followed by a sharp drop into the non-significant region. For the AR/1 process, you should observe a single significant spike at lag 1, and then all subsequent lags should fall within the confidence interval, indicating a sharp cutoff. Simulating an AR/2 process. An AR/2 process is defined as code snippet. Let's simulate one with coefficients code snippet and code snippet. Download the code on one PageCode Substack. Here, we simply provide an array with two coefficients to the code snippet argument, representing code snippet and code snippet. Now, let's plot the PACF of our simulated AR/2 series. Download the code on one PageCode Substack. For the AR/2 process, you should see two significant spikes at lags 1 and 2, and then the PACF should cut off, with all subsequent lags falling within the confidence interval. This behavior confirms that the PACF is an effective tool for identifying the order of a pure AR process, confirming stationarity of simulated AR processes. Before applying PACF, it's crucial that our time series is stationary. For UR simulated AR processes, we define them with coefficients that ensure stationarity. However, it's good practice to verify this. We can use the Augmented Dickey-Fuller ADF test, which we discussed in previous sections. Download the code on one PageCode Substack. Running this code for the simulated AR/2 series should yield a very small p-value, typically much less than 0.05, confirming its stationarity. This reinforces the principle that PACF analysis is most reliable when applied to stationary data. A special case worth noting is the random walk, which can be seen as an AR/1 process where code snippet. In this specific scenario, the code snippet coefficient leads to a unit root, making the process non-stationary. A unit root indicates that shocks to the system persist indefinitely, causing the series to wander without a fixed mean or variance. This is why a random walk's ACF decays very slowly, and its PACF might also not show a clear cutoff, highlighting the importance of ensuring stationarity before applying these diagnostic tools. Applying PACF to real-world data. Foot traffic example. Now, let's apply our knowledge of PACF to the code snippet dataset. Recall from previous sections that we likely had to difference the code snippet series to achieve stationarity. We will assume that code snippet is already available from previous steps. If not, you would typically load your data and perform differencing as necessary. Download the code on one PageCode Substack. After running this code, carefully examine the PACF plot for the code snippet series. Look for a lag code snippet where the partial autocorrelations are significant, extend beyond the shaded region, for lags 1 through code snippet, and then abruptly become non-significant, fall within the shaded region, for lags greater than code snippet. Based on the typical behavior of foot traffic data, which often shows dependence on recent past values, you might observe a significant spike at lag 1 and possibly lag 2, with subsequent lags falling into the non-significant region. For instance, if only the spike at lag 1 is significant, it suggests an AR/1 process. If spikes at both lag 1 and lag 2 are significant, followed by non-significant spikes, it suggests an AR/2 process. This visual inspection is a crucial step in the Box-Jenkins methodology for time series model identification. Broader practical applications. The identification of AR processes using PACF is a fundamental skill in time series analysis and has wide-ranging applications across various domains. Economics, modeling GDP growth, inflation rates, or unemployment, where current values are often influenced by values from previous quarters or years. Finance, analyzing stock returns or volatility, although financial time series often exhibit more complex behaviors, e.g., ARCH/GRCH effects. Environmental science, forecasting temperature, rainfall, or pollution levels, which tend to have strong autoregressive component. Engineering, predicting sensor readings in control systems or analyzing signal processing data. By mastering the interpretation of PACF plots, you gain a powerful tool for understanding the underlying structure of many real-world time series and building accurate forecasting models. Forecasting an autoregressive process. Having defined what an autoregressive process is and explored methods for identifying its order, the next crucial step is to apply this knowledge to forecast future values of a time series. This section will guide you through a complete end-to-end workflow for forecasting with an ARP model, including data preparation, implementing a robust rolling forecast strategy, fitting the model, evaluating its performance, and transforming the forecast back to their original scale for practical interpretability. Data preparation for time series forecasting. Before any model fitting can occur, the data must be appropriately prepared. This involves ensuring stationarity, which we addressed in previous sections through differencing and splitting the data into training and testing sets. A proper train-test split is paramount in time series forecasting to prevent data leakage and provide an honest evaluation of the model's out-of-sample performance. For our example, we will continue using the code snippet dataset, which represents average weekly foot traffic. Recall that we previously determined this series was non-stationary and required first-order differencing to achieve stationarity. First, let's load the data and apply the differencing transformation. We will also set a random seed for reproducibility. Download the code on one PACF Substack. The code above initializes our environment by importing necessary libraries and setting a random seed to ensure that any stochastic processes, like model initialization or optimization, yield consistent results. We then load our code snippet dataset, parsing the date column as the index. The core transformation here is applying a first-order difference using code snippet, which calculates the difference between consecutive observations. This is crucial because our previous analysis identified that the original series was non-stationary, and differencing helps stabilize the mean by removing trends. The resulting code snippet from the first difference is dropped, leaving us with a stationary series code snippet ready for modeling. Next, we split the difference data into training and testing sets. A common practice in time series forecasting is to use a fixed number of recent observations for the test set, representing a specific period for which forecasts are needed. For weekly data, a 52-week test set is often chosen to represent a full year of forecasting, allowing for evaluation across an entire annual cycle. Download the code on one PACF Substack. Here, we define code snippet as 52, signifying 1 year's worth of weekly data for our test set. We then perform a chronological split. Code snippet contains all data points except the last 52, and code snippet contains only the last 52. This ensures that our model is trained only on past data and evaluated on unseen future data. We also create corresponding code snippet and code snippet splits of the non-differenced data, which will be essential when we perform the inverse transformation of our forecasts. Visualizing the train test split helps confirm that the separation is correct and provides a visual context of the data used for training versus evaluation. Download the code on one PACF Substack. This visualization generates two subplots. The top subplot shows the original foot traffic data, clearly distinguishing between the blue training data and the orange test data. This helps us see the overall trend and seasonality, if any, in the full series. The bottom subplot displays the difference data, where the series appears more stationary, with the green training data and red test data. The gray shaded area explicitly highlights the test period, making it immediately clear which part of the data will be used for forecasting evaluation. Introducing the code snippet model for autoregressive processes. For fitting autoregressive AR models in Python, the code snippet library provides the code snippet class, seasonal autoregressive integrated moving average with exogenous regressors. While its name suggests a more complex model, code snippet is highly versatile and can be configured to represent simpler models like a pure ARP process. When using code snippet for an ARP model, we specify the code snippet parameter as a tuple code snippet. Code snippet. The order of the autoregressive AR part. This is the number of lagged observations to include in the model. Code snippet T. The order of differencing I for integrated. This specifies the number of non-seasonal differences needed to make the series stationary. Code snippet. The order of the moving average MA part. This is the number of lagged forecast errors in the prediction equation. Since we have already performed first-order differencing on our data, meaning our input data code snippet is already stationary, we set code snippet. Also, because we're specifically building a pure AR model and not including any moving average components, we set code snippet. Therefore, for an AR3 model on pre-difference data, the code snippet parameter will be code snippet. The code snippet parameter in the code snippet method is used to suppress the convergence messages that code snippet prints during the optimization process. This keeps the output cleaner, especially within loops. Forecasting strategy. Rolling window prediction. Time series forecasting often employs a rolling window or walk-forward validation strategy. Instead of training a model once on a fixed training set and predicting the entire test set, a rolling forecast involves 1. Training the model on an initial segment of the data. 2. Making a prediction for the next one or more steps. 3. Adding the actual observed values to the training set. 4. Retraining the model and repeating the process. This approach is crucial for several reasons. Adaptability to evolving patterns, economic conditions, consumer behavior, and other factors CA. And change over time. Retraining the model with the latest available data allows it to adapt to recent trends and shifts, potentially improving forecast accuracy. Realistic evaluation. It mimics how forecasts are made in a real-world scenario where new data becomes available over time and models are periodically updated. Robustness. It provides a more robust estimate of model performance than a single train test split, as it evaluates the model across multiple points in time. Computational considerations. The main drawback of rolling forecasts is their computational cost. Retraining the model at each step can be very time-consuming, especially for large datasets, complex models, or long test periods. For practical applications, a balance must be struck between the desired adaptability and computational feasibility. This might involve retraining less frequently, e.g., weekly or monthly, or using simpler models for very frequent updates. Implementing the rolling forecast function. We will create a generalized code snippet function that can apply different forecasting methods, a historical mean baseline, a last value baseline, and our AR3 model. This function will iterate through the test set, updating the training data and making predictions at each step. Let's define the function structure and the initial setup for handling different forecasting methods. Download the code on OnePageCode Substack. This code snippet function is the heart of our forecasting strategy. It takes code snippet, the code snippet, e.g., mean last, AR, the AR code snippet, and the code snippet size, how many steps to predict at once before updating history. The function initializes code snippet with the code snippet and an empty code snippet list. It then loops through the code snippet in increments of code snippet. Inside the loop, it branches based on the code snippet. If code snippet, it calculates the mean of the current code snippet and uses it as the forecast for the entire window. This serves as a simple but effective baseline. If code snippet, it takes the last value from the current code snippet and uses it as the forecast. This is another common baseline, particularly useful for random walk-like series. If code snippet, this is where the code snippet model comes into play. It fits a code snippet model with the specified code snippet, e.g., code snippet, to the current code snippet. Code snippet and code snippet are set to provide more flexibility during model fitting, especially when dealing with smaller history windows in a rolling forecast. After fitting, code snippet is used to generate forecasts. The code snippet and code snippet parameters for code snippet are crucial. They specify the indices relative to the full data series, including current code snippet. Since code snippet grows, code snippet is code snippet, the next point after the current history, and code snippet is code snippet, the last point of the prediction win. DAO. Code snippet keeps the console clean. After generating forecasts for the current code snippet, these forecasts are added to the code snippet list. Crucially, the actual observed values from the code snippet for that window are then appended to the code snippet. This walk-forward mechanism ensures that the model is always trained on the most up-to-date information available, mimicking a real-world forecasting scenario. Executing the rolling forecasts. Now we can use our code snippet function to generate predictions for our test set using the different methods. Download the code on one PACF substack. In this step, we define our code snippet as code snippet for an AR3 model on difference data and set a code snippet of 1, meaning we'll predict one step ahead at each iteration. We then call code snippet 3 times, once for the mean baseline, once for the last value baseline, and finally for our AR method. The output confirms that the correct number of forecasts, equal to the test set size, has been generated for the AR3 model. Evaluating forecasts on difference data. Before undifferencing, it's useful to visualize and evaluate the forecasts on the difference scale. This directly assesses how well the model captures the short-term changes in the series. Download the code on one PACF substack. The plot visually compares the actual differenced foot traffic against the forecasts generated by the mean baseline, last value baseline, and the AR3 model. This allows for a qualitative assessment of how well each method tracks the fluctuations. Quantitatively, we calculate the mean squared error, MSE, for each forecasting method on the difference data. MSE penalizes larger errors more heavily and is useful for comparing model performance. A lower MSE indicates a better fit to the difference series. From the output, we can observe whether the AR3 model significantly outperforms the simple baselines in capturing the dynamics of the difference series. Inverse transformation, undifferencing forecasts. For business interpretation and practical use, forecasts need to be on the original scale of the data. Since we difference the data to achieve stationarity, we must now reverse this transformation, a process known as undifferencing or inverse differencing. The inverse of first-order differencing is a cumulative sum, but it requires a starting point. The starting point for undifferencing a one-step-ahead forecast is the last known original value from the training set. For subsequent forecasts, the previous undifferenced forecast acts as the starting point. Let's create a helper function for this common operation. Download the code on one PACF substack. The code snippet function takes the last value of the original training series, code snippet, as its starting point. It then iteratively adds each code snippet to the previously undifferenced value. This cumulative sum operation effectively reverses the differencing. E function returns the undifferenced forecasts, excluding the initial seed value. Now, let's apply this function to our AR3 model's difference forecasts. Download the code on one PACF substack. We retrieve the code snippet from our code snippet dataset. This value is crucial as it anchors our undifferencing process. We then pass this value along with the code snippet to our code snippet helper function. The output confirms the first few undifferenced forecasts and the total number of forecasts generated, which should match the length of our test set. Evaluating forecasts on original scale data. Finally, we visualize and evaluate the AR3 model's forecasts on the original scale. For business applications, mean absolute error, ME, is often preferred as an evaluation metric on the original scale because its units are the same as the original data, making it directly interpretable. Download the code on one PACF substack. The plot provides a visual comparison of the actual original foot traffic values against the undifferenced AR3 forecasts. This allows us to see how well the model's predictions align with the original data's patterns, including any trends or seasonality that were implicitly captured by the differencing and subsequent undifferencing. The mean absolute error, MAE, is calculated for the undifference forecasts. MAE is particularly valuable in a business context because it represents the average magnitude of the errors in the same units as the origin. NAL data. For example, if the MAE is 3.45 people, it means that, on average, our forecast for weekly foot traffic is off by approximately 3 to 4 people. This provides a direct, actionable insight for a store manager. They know that their staffing plans, inventory levels, or promotional schedules might be off by this average amount, allowing them to build in appropriate buffers or contingencies. Advanced model insights and diagnostics. While the code snippet model fits quietly with code snippet, it provides a wealth of information through its summary. Displaying the model's summary after fitting can offer deeper insights into the model's coefficients, statistical significance, and overall fit. Download the code on OnePageCode Substack. The code snippet output is a comprehensive table. Key sections to examine include coefficients. These are the estimated $/$5 values for each AR lag, e.g., code snippet, code snippet, code snippet. Their code snippet values indicate their statistical significance. Typically, p-values less than 0.05 suggest significance. Standard errors. Measure the precision of the coefficient estimates. Log likelihood, AIC, BC. Information criteria used for model comparison. Lower values generally indicate a better fit. Ljung box. Cue a test for autocorrelation in the residuals. A high p-value suggests that the residuals are white noise, indicating a good model fit. Jarkbera, JB, a test for normality of residuals. Understanding these diagnostics helps confirm if the AR model adequately captures the underlying patterns and if its assumptions, like white noise residuals, are met. Beyond point forecasts, it's often useful to quantify the uncertainty around predictions using prediction intervals. These intervals provide a range within which the actual value is expected to fall with a certain probability, e.g., 95%. Download the code on OnePageCode Substack. The code snippet method, when called without specifying code snippet, which is the default for one-step-ahead forecasts after the training period, provides the point forecasts along with their standard errors. By specifying code snippet, we request a 95% confidence interval. Just like the point forecasts, these lower and upper bounds of the confidence interval also need to be undifferenced to be meaningful on the original scale. The plot visually represents this uncertainty, showing the forecasted line surrounded by a shaded region representing the 95% prediction interval. This helps stakeholders understand the potential range of future values, not just a single point estimate. Limitations and considerations for AR models. While effective for certain types of time series, autoregressive models have limitations. Linearity assumption. AR models assume a linear relationship between the current observation and past observations. Nonlinear patterns will not be captured effectively. Constant variance. AR models assume the variance of the residuals is constant over time. Homoscedasticity. If the series exhibits changing volatility, AR models may not be optimal. No seasonality. Pure AR. A pure AR-P model does not inherently handle seasonality. If strong seasonal patterns are present, a seasonal AR, SAR, component, or a SARIMA model, which includes seasonal differencing and seasonal AR/MA terms, would be more appropriate. Stationarity requirement. The core assumption is that the underlying process is stationary or made stationary through differencing. Failure to achieve stationarity can lead to unreliable forecasts and invalid statistical inferences. Parameter selection. Choosing the correct order code snippet can be challenging, even with tools like PACF. It often involves a combination of statistical tests, information criteria, AIC/BEC, and domain knowledge. AR models are particularly effective when the time series exhibits strong, decaying autocorrelation, suggesting that past values directly influence future values in a linear fashion. They are less suitable for series with strong moving average components, where past errors are more influential, pronounced seasonality, or nonlinear dynamics. In such cases, extending to ARIMA, SARIMA, or more advanced models might be necessary. Summary. This chapter has provided a comprehensive exploration of autoregressive AR processes, a fundamental building block in time series analysis. We've delved into their theoretical underpinnings, characteristic behaviors, and, critically, the practical methods for identifying their order. This section serves as a concise recap, reinforcing the core concepts and identification techniques. Defining autoregressive processes. An autoregressive AR process models the current value of a time series as a linear combination of its own past values, plus a white noise error term. This means that the series is regressing on itself. The order of an AR process, denoted as code snippet, specifies how many previous time steps influence the current value. The general mathematical form of a stationary autoregressive process of order code snippet, or code snippet, is given by code snippet. Let's break down each component. Code snippet. The value of the time series at the current time code snippet. Code snippet. A constant term, representing the intercept or baseline level of the series. Code snippet. These are the autoregressive coefficients. They quantify the linear impact of each past value, code snippet, code snippet, code snippet, on the current value code snippet. For a stationary AR process, these coefficients must satisfy certain conditions, e.g., the roots of the characteristic polynomial must lie outside the unit circle. Code snippet, the values of the time series. ES at previous time steps, lags. Code snippet, the white noise error term at time code snippet. This represents the random, unpredictable part of the series that cannot be explained by its past values. It is assumed to be independently and identically distributed, ID, with a mean of 0 and a constant variance. Identifying the order of an AR process, ACF and PACF. The primary tools for identifying the order code snippet of an code snippet process are the autocorrelation function, ACF, and the partial autocorrelation function, PACF, plots. Understanding their characteristic behaviors is crucial for model selection. Autocorrelation function, ACF, behavior. For an code snippet process, the ACF typically exhibits a slow, gradual decay towards 0. This decay can be exponential or sinusoidal, but it does not cut off abruptly. Why it decays? In an AR process, the current value code snippet is directly influenced by code snippet, which in turn is influenced by code snippet, and so on. This creates an indirect, cascading correlation across many lags. For example, code snippet is directly correlated with code snippet and indirectly correlated with code snippet through code snippet. This indirect influence persists across many lags, causing the ACF to slowly diminish rather than suddenly drop. Contrast with MA processes. This behavior is a key differentiator from moving average, MA, processes. For an code snippet process, the ACF will cut off abruptly after lag code snip. This contrast is a powerful diagnostic tool. If the ACF decays and the PACF cuts off, it's likely an AR process. Partial Autocorrelation Function, PACF behavior. The Partial Autocorrelation Function, PACF, measures the correlation between code snippet and code snippet after removing the linear dependence of code snippet on intermediate observations code snippet. This purified correlation is precisely what we need to identify the direct relationships in an AR process. For an code snippet process, the PACF will show significant spikes at the first code snippet lags and then cut off abruptly to 0 or become statistically insignificant after lag code snippet. Why it cuts off? Because the PACF isolates the direct correlation, it reveals exactly how many past terms are directly influencing the current value. In an code snippet process, only the first code snippet lags have a direct influence. Any correlation beyond lag code snippet is due to the indirect effects already captured by the previous code snippet terms. Once these indirect effects are removed by the partialization, the PACF effectively becomes 0 for lags greater than code snippet. Practical demonstration. Simulating and identifying an AR2 process. To solidify our understanding, let's simulate an code snippet process and observe its ACF and PACF plots. This will visually confirm the characteristic behaviors we've discussed. First, we import the necessary libraries. Download the code on OnePageCode. Substack. Code snippet is used for numerical operations, especially for generating random numbers. Code snippet is for plotting our time series, and it's ACF/PACF. Code snippet from code snippet is a convenient function to simulate ARMA, and thus AR, processes. Code snippet and code snippet are specialized code snippet functions for plotting autocorrelation and partial autocorrelation functions, respectively. Next, we define the parameters for our AR2 process. Download the code on OnePageCode Substack. Code snippet. This array contains the autoregressive coefficients. Code snippet means code snippet and code snippet. Note that code snippet expects the coefficients with a negative sign if they are on the right-hand side of the equation, i.e., code snippet. So, we'll pass code snippet to the function. Code snippet. Since we're simulating a pure AR process, there are no moving average components, so we pass code snippet, or code snippet. Code snippet will generate 500 data points to ensure we have a sufficiently long series for reliable ACF/PACF estimation. Now, we generate the AR2 time series. Download the code on OnePageCode Substack. Code snippet. This is a crucial detail for code snippet. The function internally represents the AR part as code snippet, where code snippet is the lag operator. So, if our coefficients are code snippet, we pass code snippet to the code snippet argument. In code snippet argument expects the characteristic polynomial. Coefficients. If code snippet, then code snippet. The code snippet argument takes code snippet. Our code snippet array already contains code snippet, so we transform it to code snippet. Code snippet. No MA terms. Code snippet. The length of the generated series. Code snippet. The standard deviation of the white noise error term. Let's visualize the generated time series to get a sense of its behavior. Download the code on OnePageCode Substack. This code block simply plots the code snippet over time, allowing us to visually inspect its fluctuations and stationarity, which is assumed for AR models. Finally, we plot the ACF and PACF to confirm their characteristic behaviors. Download the code on OnePageCode Substack. Code snippet creates a figure with two subplots side by side for ACF and PACF. Code snippet plots the ACF for code snippet on the first subplot, showing up to 20 lags. Code snippet plots the PACF for code snippet on the second subplot, also up to 20 lags. The code snippet specifies the Yule-Walker method for PACF estimation, which is common. Code snippet adjusts subplot parameters for a tight layout. When you run this code, you will observe ACF plot. The bars will typically show a statistically significant correlation at initial lags, and then gradually decay, often oscillating, but not abruptly cutting off. PACF plot. You should see two significant spikes at lag 1 and lag 2, corresponding to code snippet, and then the bars FO. Our subsequent lags should fall within the blue shaded region, indicating they are not statistically significant, effectively cutting off after lag 2. This confirms the AR2 nature of the simulated process. Conclusion and next steps. This summary has reinforced that autoregressive processes model a series based on its own past values, characterized by a decaying ACF and a cutting off PACF. The order code snippet of an encode snippet model is directly identifiable from the lag where the PACF cuts off. Successfully identifying the order of an AR process is a critical step in time series modeling, as it directly informs the structure of the code snippet, autoregressive integrated moving average, or code snippet, autoregressive moving average with exogenous inputs, models you will build for forecasting. Remember that these identification steps are often iterative and require careful consideration of both statistical significance and domain knowledge. Always ensure your series is stationary before applying these identification techniques.